pointer to the structure itself. And what happens is the interpreter, when it gets invoked, gets a funny value in its global offset table register. So it basically goes ahead and uses that to find the real global offset table pointer, which is somewhere down in the other stuff, and then also extracts the pointer to the code that it's supposed to interpret. And that's a small number of instructions overhead on the way into the interpreter, like 2 or 3, and just not a big deal. Object headers. Okay, now we get to the more garbage collector related issues. If we look at what happens inside a JVM, again, I'm not familiar enough with CLR here really. Java objects tend to have more header information than C++ objects. So typically there's some locking information, maybe some hash coding information and so on. That's actually not a real compatibility issue, I think, in going between this generated, the VM generated code and native code, since you can essentially view these extra fields as just something that's, say, part of comp.lang.object, but the comp.lang.object class from which everything inherits, and everything looks basically like a kosher C++ object anyway. On the other hand, it's actually possible to avoid this header, and if we look at what happens in GCJ on most platforms these days, in fact, objects look almost exactly like C++ objects. The only header information is the virtual function table pointer. Yeah, I'm not sure I want to spend time on the rest of this. Okay, so I want to say a little bit about garbage collection here. The major obstacle to intercallability often is the fact that virtual machines require pointer location information for everything that runs within the virtual machine. So for objects in the heap, for static data, and generally also for function frames, at least for call sites within those well, the function frame information in general, where pointers are located in a function frame, is going to depend on the particular code point at which that function is executing. Generally, most implementations keep this information only at call sites and at save points, and those are the only places where it's possible to run a garbage collection. It is necessary in general to insert enough save points so that you can guarantee that you can get to one in about an amount of time. This, of course, is something that's not required by the standard C and C++ ABI, and that normally generated C and C++ code doesn't obey, and therefore it's very difficult to call C and C++ code directly. It turns out that even if you went through the thought exercise and assumed that you made all the C and C++ compilers understand Java conventions and actually generate pointer location information, this is hard to do. The features in C that actually get most in the way here are the fact that you have unions which may contain pointers, so you can't really tell dynamically, you can't really tell statically whether or not there's a pointer in a particular location. And furthermore, you can pass around pointers to those particular fields. So even if you try to dynamically tag these unions to figure out whether they contain a pointer or not, you really can't. So as a result of this, it's necessary that in order to be able to run the C and C++ code within this managed or VM environment, it's necessary to somehow fake up the C and C++ frames, to have some other mechanism for keeping track of pointers that might be contained inside these frames. Okay, there's several alternatives here, most of which I think are pretty well known, so I'll go through these really quickly. We can avoid this problem with a completely conservative GC, in which case we no longer need pointer location information on the Java or CLI side. That only requires some minimal C compiler cooperation, and in fact the way that really seems to work is that C compilers really don't cooperate in this way. So at least in the way of GCC, I think this is sort of unofficially a bug. On the other hand, it'll get fixed once anybody encounters it in practice, and it hasn't happened yet. So the problem with doing this, if you scan for pointers conservatively everywhere, is that you may in fact end up retaining more memory. So for the examples that Boehm3 and Wurzel and Henkel used, in fact, they saw something like up to 60% increase in live data size as a result of this. And it turns out most of the information that you actually, the most critical information that you lose as part of this is not so much, so what's an integer versus what's a pointer, but it's what's live at a particular, what pointers are live at a particular point. And that can cause additional memory to be retained. An additional cost of this is that it becomes impossible to compact at all in this environment. Since you don't know for sure that any particular thing is a pointer, you can't safely move the thing it points to. You also very often, with completely conservative garbage collectors, end up with a fairly large root set because you end up having to scan lots of memory for potential pointers. And there's potentially some overhead here in identifying pointers, though it's not clear that that's real. But the interesting thing is, in avoiding this problem, we're actually on a continuum here. That's the extreme case, which I think is reasonably well known, that we scan everything conservatively for pointers. Anything that might be a pointer is considered to be a pointer anywhere in memory. On the other hand, we can fairly gracefully actually supply some type information to the garbage collector in this context, so long as we leave that type information optional so that existing C and C++ code can fail to supply it, everything still works correctly. So if we look at, for example, what happens now in GCJ and Mono, they have precise type information. The garbage collector has precise type information on objects located in the heap, but it doesn't have type information located either in static data or on the stacks. Oops, actually there's a mistake in the slides here. That should be 60% because I was citing an older paper here than in the previous slide. But in any case, the effect on memory retention here in the typical case is essentially 0. The disadvantages are essentially the same, though we actually do get some additional guarantee here, which is that unbounded memory retention, the case where memory retention is unbounded, can only occur in certain rare cases which we can actually test for.
But is that 39% accurate or wrong?
That's wrong. It's actually, it should be the same number. The important thing is it's the same number on the preceding slide. They reported 39% in one paper, which was looking only at type accuracy information, and they reported 60% in a later paper, which included liveness information. So it's not, the 60% is probably not really achievable because it assumed very good liveness information, which is probably better than what JVMs with type descriptors actually get. So, so the truth is somewhere in that range.
Okay. And you're saying that the extra type information doesn't really help in this sense?
The extra type information in this sense doesn't help. In the worst case sense, it does help, right, because basically there's a certain failure mode that's precluded by doing this, which is probably the more common of the failure modes here, where you really get unbounded memory retention. Plus the remaining failure mode is one that you can test for. Okay, I'm pretty much out of time here. I was going to talk about yet another possibility here, which is completely minimally conservative. So let me just go straight to the next slide, to the pictorial representation here, where we're basically, the green sections are the ones that are scanned precisely, for which we have type information. The red sections are the ones that we're not. And the idea here is that basically we supply, the basic idea here is that really, in some sense, the two of them are providing exact type information and conservative collection are complementary, in that what causes the problem with conservative garbage collection is essentially long-term stable data, which causes us to retain additional memory. On the other hand, those are precisely the pieces of data for which it's actually relatively cheap to provide type information. The ones for which we don't want to specify type descriptors are the ones that change rapidly. And in this particular case, we actually go to the extreme case of providing type information for every piece of Java code except stuff that's changing rapidly inside loops. And if by not specifying that, we get rid of the necessity to have save points. On the other hand, we get actually some fairly strong properties out of this. So in particular,